We're looking at section 7.1, which covers the introduction to Pythagorean Theorem. Pythagorean Theorem reads, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the leg. So let's write out what that says. That says the hypotenuse squared is equal to the sum of the squares of the length of the legs. So let's say leg 1 squared plus leg 2 squared. So if we have a right triangle, we have this relationship exists. Now to review, hypotenuse means the side opposite the right angle. That would be our longest side in that triangle. The legs would be the ones adjacent to the right angle, or the two shorter legs. Doesn't matter which order we write them in, leg 1 or leg 2. Since we are adding them, that we can vary on how we set that up. But hypotenuse squared equals leg 1 squared plus leg 2 squared. So let's plug in some values we have. We can talk about them by sides. Hypotenuse would be AB. I could call one of the legs AC. And one of the legs, let's go BC. Now, if we look at this one, and now plug in those names we have for sides, we get C squared equals B squared plus A squared, which looks very similar to C squared equals A squared plus B squared, which may likely be the way you originally saw Pythagorean theorem, C squared equals A squared plus B squared. And we may at times refer to it as that, but it's important we remember hypotenuse squared equals leg squared plus leg squared. It comes back to that hypotenuse being by itself. It always has to be by itself. It has to be the longest side by itself and the other two adding up. If not, it's not going to work. We have to be careful with this A squared plus B squared equals C squared, because what if I took these letters and rotated them around and suddenly made A the hypotenuse? If all we know it by is the letters, we'll get stuck and we may make a mistake. So we need to know hypotenuse by itself. So let's jump in and try some problems looking at our Pythagorean theorem. Our first one, we have our right triangle here. We need to find x. 3 and 5 are our given sides. 3 is the leg. 5 is the hypotenuse. So we said earlier it's hypotenuse squared equals leg squared plus leg squared. And this will be leg 1 and 2. We just want to make sure we keep them separate. So I get 5 squared equals x squared plus 3 squared. If I square the values I have, I get 25 equals x squared plus 9. Subtract 9 from both sides to get the x squared by itself. I get 16 equals x squared. Take the square root, and I get x is 4. So the length of my leg is 4. The next one we look at, here we're looking at the hypotenuse. That's that longest side. So we have to be careful when we set it up. The hypotenuse, which is our x, is by itself. That's equal to the leg plus the other leg squared. 4 squared plus 6 squared. So x squared equals 16 plus 36. Combine those, I get x squared equals 52. Take the square root of both, I get x equals radical 52. Now, it isn't a perfect square, so it will be as a radical, but we have to get in the habit of simplifying our radicals. Well, if I look at 52, the factors of 52 is, well, it's even, so it's 2 and 26. I can break down the 26, because that's even, to 2 and 13. So now I have 2, 2, 13. Each of those is prime. So if I look here, 2's, I can group those together. I'm going to take those 2 out of my radical, because it's really 2 squared, and I can take that out, and it becomes 2 radical 13. So the length of my hypotenuse in this case is 2 radical 13. And if we check it on our calculator here, that's about 7.2. Now, what that shows us here, 7.2, it does turn out to be the longest side, which it should be bigger than 4 and 6. If it didn't, we didn't set it up correctly. Also, we're going to usually leave it in simplified radical form. We're not going to have to worry about the decimals. You may have the occasional homework problem that wants the decimals, but we're going to want to just leave it simplified radical form. It's nice if we can check with the calculator just to know an idea of what 2 radical 13 is, because sometimes it's tough with those radicals, but leave it in simplified radical form and you'll be fine. So let's look at a couple more examples here. Still looking for x. So in our first one, I have 9 and 12. That's my hypotenuse that I'm searching for. So that's x squared equals 9 squared plus 12 squared. I get x squared equals 81 plus 144. Combine those, I get x squared equals 225. The square root of both of those, square root of 225, well, 225 happens to be a perfect square. It is 15. So length of my hypotenuse is 15. We'll call it 15 inches because that fits the units we have. It is the longest side, so we're good. Next one, we have x squared, hypotenuse again, equals 14 squared plus 48 squared. If I square 14, I get 196. If I square 48, 2,304. Probably don't have that one memorized. That's okay. We combine those two, and we get 2,500 equals x squared. I take the square root of that. And if we look, okay, well, what's the square root of 25? That's going to be 5. And if we have those 2 zeros there, our square root is going to be 50. So x would be 50 centimeters, and that would be the length of our hypotenuse. Now, let's see how we may see this Pythagorean theorem kind of disguised in other problems. So, now we have to find the area of an isosceles triangle with side lengths 10 meters, 13 meters, and 13 meters. So here's my two sides in the isosceles, and 10 is the side that's not congruent. Area of a triangle is 1/2 base times height, which in our triangle, height and base are perpendicular values we have here. So we need to find the area of this triangle. What we know our base is 10. 13 is not the height. The height here would actually be what we've called in previous chapters the altitude. Well, if we notice in this isosceles triangle, we can actually cut it down the middle, and that gives us 2 equal parts. So let's redraw that half of it as 13 here. This is height, which I'm going to solve for. And this value is going to be half of that base, so 5. So now I can find my height using Pythagorean theorem for this triangle, which will be the height for my original triangle, which will then let me find the area. So we look here, our hypotenuse is 13, so 13 squared equals 5 squared plus h squared. 13 squared is 169 equals 25 plus h squared. If I subtract 25, I get 144 equals h squared. And we could probably see here we're going to take the square root of both sides, and our height comes out to be 12. So now we have our triangle, base of 10, height of 12. So our area is going to be 1/2 10 times 12. That's going to be 1/2 of 120, which is 60 meters squared. So yes, we haven't done much with area, but we'll also see that Pythagorean theorem does come up there, which really shows and really gives us the importance of how Pythagorean theorem is going to be spread out throughout the rest of the year, and how it's a very important principle in our class. Now, one last term we have is the Pythagorean triple. If you've noticed on some of the answers we've had, they come out nicely when we solve the problem with Pythagorean theorem. If we jump back here, on the first example page we got a 4 as a solution. 2 radical 13 came out as a radical, didn't come out as nice. The next page, 15, 50, those came out nice. This one I got a 12. They came out as whole numbers. These are actually sets. These are parts of numbers of a Pythagorean triple. And these are nice. So a Pythagorean triple is a set of three positive integers, a, b, and c, that satisfy the equation c squared equals a squared plus b squared, or Pythagorean theorem. Now, we could have an infinite amount of numbers that work for Pythagorean theorem that form a right triangle. We just happen to have some numbers that are all whole numbers when they work. The most basic one we have is 3, 4, 5. Some other ones, 5, 12, 13, 8, 15, 17, 7, 24, 25, and we could go on from there. But these are really the four smallest Pythagorean triple sets. And these are nice, because maybe you start to recognize, maybe just the first two. As you go through a problem later that uses Pythagorean theorem, if you just recognize, okay, this is a Pythagorean triple or a different form of it, it may save you some time or prevent you from making errors. What makes these nicer, though, is I can also look at their multiples. If I multiplied this by 2, I got 6, 8, 10. Well, 6, 8, 10 would work as a Pythagorean triple because 10 squared equals 8 squared plus 6 squared, or 100 equals 100. I could also multiply them by 3, 9, 12, 15. Maybe by 10, 3, or 30, 40, 50. And it's really any multiple of those numbers would work for Pythagorean triples. Same idea, 5, 12, 13, I can multiply them by 10, or multiply them by 2, I should say. 10, 24, 26. I can multiply 8, 15, 17 by any multiple, as well as 7, 24, and 25. So these are not the only Pythagorean triples. These happen to be the four smallest, the ones we'll see most often, and we may see them in different forms like 9, 12, 15. But they're just numbers that make it easier. They give us whole numbers. I don't have to have whole numbers here. We can get radicals, and we're going to see later on in next section where we actually start off with radicals and we have to solve with them. But these are just nice ones we happen to have.